Okay, so I think we can start. So the webinar starts right now. So hello everybody, this is Luboš Pirkl from CFD Support. Welcome to the webinar about fun design and simulation workflow by CFturbo and TCFD. In today's webinar, we would like to show you a way how to design a centrifugal fan from scratch in CFturbo, and then how to simulate it and evaluate it in TCFD. I hope everything works well. We are running live, so in case of any technical problems, feel free to contact us and we will gladly answer all your questions and comments. The webinar is being recorded and its recording will be made publicly available. At the end of this webinar, there will be a Q&A session dedicated to your questions and our answers, so feel free to ask your questions. You can ask them anytime during the webinar, and at the end we will come to the Q&A. We will answer some of your questions, and some of them will be answered later via email. So I think all is set. So it's time to get to the action. So let's move. So yeah, so to avoid any misunderstanding, right in the beginning, I would like to stress out that this is a two-way webinar of two independent companies. We have synergy products, and we would like to show you how well they work together. So both of them are standalone tools, independent on the other. I guess you know, but still, CFturbo is a German company that produces a turbomachinery design tool called CFturbo, the same name. And CFD Support is Czech company that produces an automated CFD tool called TCFD. So yeah, so this is the brand info. Please let me introduce the webinar speakers. So this is me. My name is Luboš Pirkl. I am co-founder of CFD Support, and my current job is telling the world about CFD Support. I am here in our Prague office with my colleague, Radek Máca. Hello, Radek. Can you hear me?
Yeah, hello, Luboš from the office next door, and hello to everyone from Prague.
Yeah. So everything seems to be ready on your side. I will only note that Radek is our head engineer and senior developer here at CFD Support. And also together on the line, there is Oliver Felde in Dresden. Hello, Oliver.
Hello, Luboš, and hello, Radek.
Yeah, hi. So we all seem to be ready for the webinar. I will only note that Oliver is Senior Manager CAE at CFturbo, and he will be speaking about CFturbo software today. Here is the webinar agenda. So the webinar is going to take about 1 hour. There will be a few sections in the webinar. After this introduction section, Oliver will briefly introduce CFturbo, and he will show us how to design a completely new centrifugal fan from scratch in CFturbo. After that, Radek will briefly introduce TCFD, and he will also show us how to set up the simulation and run the simulation, and perhaps, I guess, evaluate the results in it. And finally, there will be a Q&A session dedicated to your questions and our answers. So feel free to ask your questions anytime during the webinar. Some questions will be answered right in the webinar. The rest will be answered later via email. So you can be sure that all the questions will be answered in the end. Okay, so I think we can really start. So Oliver, will you tell us about CFturbo now?
Yes, I will. Thank you, Luboš. Well, CFturbo is a German company that produces that turbomachinery design package, which we call a conceptual design package, because it's based on latest design theory for the turbomachinery design. And what you can do with that tool is you can almost design any of the turbomachinery machines that are out there. Right now, we have more than 200 active clients globally, and the modules I just talked shortly about are those for pumps, both centrifugal as well as axial. We have fans and blowers, we have compressors and turbines, and of course we have the complementary components for those machines, which are stators and diffusers, and of course volutes. We serve those industries that are given here. Amongst them, there are aerospace, automotive, consumer products, and so on and so on, and also the semiconductor industry, because that might be interesting for today's webinar. There are a lot of fans that are used in that industry sector.
Okay, so I think maybe it's time to switch to hand over the presentation to you, Oliver. So I'll do that right now.
Okay.
Yes.
All right. Okay. What you see here is the desktop, if you like, of CFturbo. If you start a design from the scratch, you have to choose from those soft buttons in order to decide which kind of machine you want to design. So today's webinar content is the design of a centrifugal fan. That's why I'm pressing the fan or ventilator button. And the very first entry or content you have to type in is the design point, because that is the point which we use for the conceptual design, and it is also the point which we think of where the machine should run in most of the time, and which we think of where it should have the best efficiency. So probably a word before I go deeper into the design. We have done this seminar or that webinar, I think 1.5 years ago. That's why this time I would like to fasten a bit, go through the first design steps a bit faster, and want to focus on some additional features which haven't been introduced so far. And if it was a bit too fast, so please check at YouTube our earlier webinar. Okay, so the design point is 38,000 cubic meter per hour. The pressure difference is 26400 Pascal, and it should run on 2,900 RPMs. Also, what you have to define is what kind of fluid you want to transport with the machine, because from that some properties are used in the design process. Here, as we consider the flow being incompressible, we just use the density. But if it comes to compressors or turbines, of course, real gas models and stuff like that are used to calculate the correct behavior and the correct thermodynamic values in certain sections. So we have a list of some predefined fluids. So for instance, high temperature or higher temperature air, which has a different density than the 20 centigrade air. And saying that, I'm done with the global setup. You see here also there are some inlet conditions given or to be defined. They are not used in the design process, but they are used later on if it comes to the CFD validation by, for instance, TCFD. Okay, once that is defined, I'm asked to add a new component. A component in the project is always either an impeller, a volute, or a stator, and the stator can be vaneless or can have blades. I'm going to start with the impeller because that's the central component of our project. And as you can see in the upper left-hand corner, there are a couple of design steps you have to run through, and you have to go through all of them step by step. But because the whole geometry is fully parameterized, you can go back at any time, can change one parameter, like the impeller diameter, can hit the OK button, and you get an update of the 3D geometry immediately. Okay, the first design step is the definition of the main dimensions. The main dimensions are just inlet diameters, outlet diameter, and outlet width. They can be typed in directly by the users, or they can be calculated by CFturbo. And when it comes to the calculation, some parameters are taken into account, as well as the solution of some 1D balance equations like continuity equation or Euler's equation of turbomachinery. So here, for instance, we use the diameter coefficient that comes from the Cordier diagram in order to make proposals for the impeller diameter. So if I, for instance, go to the automatic mode, which means at any time after a parameter change, the main dimensions are newly calculated, then you see on the right-hand side immediately how, with a change of the diameter coefficient, the impeller dimension will be changed. Okay, but I'm going to take off that checkbox, and because I know what kind of shaft diameter I want to have, which is 100 millimeter, I type in that directly, and also I'm going to get rid of that decimal places. Okay, so once that is I'm finished with that initial design, I can hit the OK button. And in our meridional view, we can see that very strange geometric shape. And that's given because we just have defined inlet diameters, the impeller diameter and the outlet width, but not yet the shape of hub and shroud. And this is going to be done in the next design step, which is the meridional contour. And that's why I go to that design step. Initially, for that centrifugal fan, we have a plain hub and a shroud that is made of a arc and a straight line. I want to change that shape at the hub to Bezier curve, and I do that by just clicking on opening that context menu. And also what I want to do, I want to introduce a certain inlet line here at the shroud, because I want to have a short piece of meridional contour which has a constant shroud radius. And again, to this end, I right click on the curve, and I'm going to add an inlet curve. That's funny. Okay, and here we are. Again, if I right click on some controls, I have an access to some extra edit boxes where I can directly set parameters, and I'm going to do that here for that inlet area. Okay, something like that. And I can do that, but also by drag and drop. And on the right hand side, you see immediately information being displayed that can be calculated of the inputs that have been done so far. Okay, 250. Okay, and then I'm fine with that initial design. Maybe I have the leading edge not at a constant radius, but almost perpendicular to hub and shroud, and that's why I'm going to change that like that. Okay, if I click OK, I see something in our 3D display, and that's just the meridional contour which is rotated, and that forms that solid here. The next step is to define first the general shape of the blades, also the number of blades, and then when that is done, the blade angles. Very often in fan design, circular 2D blades are used because manufacturers used to take metal, sheets, bend them, and weld them together, and that's it. And that's why that is one of the shapes available, but there are, of course, others as well. So if you choose, for instance, freeform 3D, then from an aerodynamic point of view, you have most of the freedom to design your impeller. But of course, you have to bear in mind how to manufacture your design. That's why I'm going to leave it on circular 2D. When it comes to that shape, then only the hub span can be manipulated by just giving him a leading and trailing edge angle, because the shape, the circular shape, will determine all the other spans, which are here just 2, but of course I can change it to up to 11 spans if that is necessary, but it's not necessary here because it's just a simple shape. Okay, once I'm happy with that, I can go directly within that design step to the next design step, but I also can click OK. Then I see in my meridional view the position of the leading edge. And the next design step then is what we call meanline design step. Here, the blade is designed with a 0 thickness because that's going to be added in the next design step. Also, what you see here is that there is nothing you can do here apart from telling where is the leading edge position in a tangential direction. And that's why, because the circular shape has already defined everything. So that's sort of speaking just for information here. But of course, if you change the blade shape to, for instance, freeform 2D or freeform 3D, then you have more freedom to change your shape and the geometry within this design step. I directly go to the next design step, which is adding the thickness onto that mean surface, as we call it, and that can be done in 2 ways, either linear by control points, and between the control points the thickness is distributed in a linear way, but it can also be freeform, where we again use Bezier curves and where we define the thickness distribution from leading edge to trailing edge. Also, if I again use the context menu, I also have access to a built-in profile manager. And in that profile manager, there are a couple of profiles predefined. So for instance, some 4-digit NACA profiles, and one can take the thickness distribution from them and can use them in the blade profiles design step. But because I think of a producer that might use metal sheets, I leave it to the linear mode where the thickness is constant from leading to trailing edge. That's why I'm going back to linear and leave it like it is. If I press OK and go back to 3D model, then what I can see is that I have sharp edges at leading and trailing edge, and that also at the trailing edge, the blade is not completely within the meridional contour. And in order to make or sort that out, I'm going into the very last design step, and here one can define the shape of the leading and trailing edge. And one shape, for instance, is the elliptic one, where one can define a half axis ratio, radius ratio, which is 3 by default here, and I'm going to change it to 2. And one can also tell that at the trailing edge, the blade should be trimmed with the impeller diameter. And I'm going to show what that means by just zoom into the blade. Okay, now it's not trimmed, and if I trim it, it's just trimmed on one side and projected at the other side, and then one gets a very nice 3D model. And by pressing OK. I'm ready with my initial design for the impeller. My second component in that webinar will be the volute, which I'm going to add at the outlet. And to this end, open that menu at the outlet, add a new volute. That volute should have a certain inlet diameter. Maybe 1,400 is a bit too big, so I'm going to change it to something like that. But the inlet width should be bigger because I want to have a rectangular shape of the volute, and to this end I need a wider inlet. Also, what I want to do is I want to have a certain axial offset. That's why I'm going to the next tab, change the offset to, for instance, 65, and that's it. So I'm done with the setup and inlet of the volute. The next design step is to choose from the built-in general cross-section shapes, and they can be various. So there we have everything apart from rectangular, and it's trapezoidal, it's round, it can be round asymmetric. You can use, again, Bezier curves and line segment curves that almost can define any kind of shape, and it also can be radius based. And above that, it don't have to be symmetric. You can also have at the left-hand side a rectangular shape, and on the other side, for instance, a round shape. But again, I'm going to leave it to default because it's a centrifugal fan, and therefore I don't have to do anything more in this design step. When I enter the next design step, I enter probably the most important design step of the volutes. And in this design step, the cross section at each angle position is scaled either according to some own experience or on the basis of some built-in rules, like the standard rule defined by Fleiderer. And here again, one can change parameters, and then one gets immediately a change of the geometry. But I'm going to leave it to Fleiderer's default swirl exponent like 1. And if I now press OK, I also have an update of the 3D geometry of the fan. But this just lacks of an outlet diffuser plus the cut water, and that's why I'm going to enter again. And I think I have that was too big. Let me just okay, and here I'm going to enter a certain outlet diffuser, which again should be rectangular, just like the volute cross section, and it should have a height of 400 and a width of 300, and maybe the length of that diffuser can be 1,000. And again, I get a lot of informational values like the cone angle, which is very small here, which is good because in order to avoid flow separation. Okay, and saying that, I'm going to enter into the very last design step for the volute, and that's the cut water. And here I choose the simple mode. I could also have different modes, but the simple mode is the one that I'm going to apply for that rectangular shape. I can tell at which angle that the cut water should be located, and I can also tell him what is the cut water height by that parameter. And once I'm pressing OK, I'm almost done with my initial design. And because it's an initial design, I have to analyze that in order to make sure that my design goal is reached. And that can be done by using a lot of implemented interfaces. Those interfaces are meant to get very quickly into any simulation environment in order to validate the design. Okay, and today it's a joint seminar between TCFD and CFturbo. That's why I'm going to choose TCFD, choose the components I want to consider in the design, and give him a name. So for instance, fan, and also tell him where to save the export. But it tells me that something is wrong, and I have to sort out that well, errors, if you like. And that's why I have to go back and have to go to the impeller again, add some extra CFD extensions, so they can be radial and can have a certain length, so for instance 10 millimeter. And also I have to connect by kind of virtual geometry the volute and the impeller. And also what I want to do is I want to introduce a fillet radius on hub and shroud, because if there is a seam or a welding seam, then there might be some fillet radius there. Okay, once I have done that, I can, well, there's a CFD setup for the volute as well, where I can add another extension if I like, and I can define the extension here. Okay, and once I have done that, I should be able to run the TCFD export, and it looks very good because everything is green. I have given him a name, I have given him a destination. I could start the export here. I even could start firing up TCFD from CFturbo, but that's something I don't want to do because that's RAD export. I just press OK here, and now a TCFD file is written with all the information necessary to run the simulation, and also all the STL data are created and exported, which are also necessary to set up the simulation run in TCFD. All right, so that probably takes a couple of more seconds. Once that is ready, Radek could start with his presentation. But before that, I would like to take the chance just to introduce another feature which probably hasn't been, or which wasn't introduced the last time, and that's the secondary flow path feature. And to this end, I'm going to add another stator at the inlet, and that should be an actual stator with a certain length. So for instance, 800 millimeter. I have to define the inlet and outlet geometry, and also need a certain gap between two adjacent components. That's why I'm introducing this actual offset here. And if I press OK, then it looks in the meridional contour like that. And this is one of the features I want to show here. It's I can also, apart from the fluid solid, I can also define what we call the material solid, and I have to do that by activating the solids. And I can do the same in the impeller, just by going through the second tab. I'll leave everything as it is. I just want to show you quickly how it would work. But the most important thing is the secondary flow path design, and that can be activated here on the third tab. And what you see here is some kind of polylines with some control points, which one can move to certain positions, and one can, by doing so, define the secondary flow path. Most important is certainly to define it here at the shroud side, because there might be, or you probably want to have some sort of a sealing in order to avoid flow going back to the suction side. And again, there is a lot of functionality in the context menu. So I'm going to split the curve here and just insert a new Bezier point. And yeah, by doing so, well, maybe that's something I should split. Okay, and once I'm finished, I can run again on the project at model finishing, because that is needed to produce all the solids. And once that is ready, I'm almost at the end. So I can now show the material solids which were generated. We just have two material solids, the inlet stator and the impeller. And we also get some information, geometric information of these solids, and they are given here, like volume, mass, center of gravity, moments of inertia, and stuff like that. So that's the material domains, but I can also show you the flow domain, which I going to cut through, and what you see here is now the negative, if you like, with all the details where the flow can, for instance, flow back over the secondary flow path and stuff like that. And again, this can be exported to TCFD, and you can then run a complete simulation of all the details you would have in a turbo machine. Okay, and saying that, I'm at the end of my presentation, and I would like to hand over to Lubos and Radek.
Okay, Oliver, thank you very much. It was very impressive, and it looks very simple and easy to how to create from scratch such a complex machine. So thank you for it. And yeah, so I'll take back the presentation. Yeah, so this was CF Turbo part, and that moves us to the turbomachinery simulation part. And yeah, and please let me start with a little description of what is TCFD. So TCFD is a comprehensive high-tech CFD code, which is focused and unlimited. It's designed to be complete CFD workflow that covers all the engineering steps in graphical interface, from the pre-processing over the simulation run to the very detailed post-processing of the results. It's independent on any other CFD software, and on the other hand, it's fully compatible with other software. And for this reason, it can be easily integrated into an existing process chain in any organization. TCFD is always focused on particular workflows, so by particular applications. So TCFD core business has always been turbomachinery simulations like pumps, fans, turbines, compressors, hydro turbines, wind turbines, and many other kinds of rotating machinery, both radial and axial machines, both compressible and incompressible fluid flows. And later, we have decided what had worked so well in turbomachinery, we have extended to external aero or even internal aero, or even, for example, to ship hydrodynamics. And yeah, so we believe TCFD is unique CFD workflow because it's unlimited, which means our clients can keep TCFD forever and they can use it for unlimited number of users, jobs, or cores. And it means our clients can scale their CFD simulations in a really big way, and they can use their resources to the fullest. Yeah, So TCFD is focused on particular applications and workflows. So for example, a FAN engineer uses the FAN inputs, FAN names, units, and results, as you can see, I believe, later in this webinar. TCFD is automated. For this reason, it's extremely effective. We have good technical support. TCFD includes a lot of real tutorials, which are based on real projects we did in the past, and also they show the best practice settings that ensure the smooth start of people who start with CFD simulations or with the beginners. And yeah, TCFD is very progressive because it successfully merged the benefits of an open source, which means that it's perpetual for unlimited number of users, jobs, and cores, and it merged the benefits of open source with the benefits of commercial codes. That means it's professionally maintained, it has graphical interface, it's robust, it's accurate, it's automated, well documented, well tested, and simply it's ready for the industry. Yeah, the user can simply put the data in and TCFD does its job, writes down the results, and in the end, the user can just pick up the final report, and that's it. So TCFD can be used either as a black box or it can be used as a fully sophisticated CFD code where all the options are opened. So the beauty of TCFD is that it's the user who decides how deep to dive into CFD or not at all. So that's, I believe, the uniqueness of TCFD. And yeah, so here I would like to hand over the presentation to Radek, who will show you how to really work and give you real experience with TCFD. So Radek, are you ready for your part of the webinar?
Yes, I am. So
okay, so right now I'm switching. I'm handing over the presentation over to you. So can you?
Okay, I already claimed it, and maybe we should wait a few seconds.
Couple of seconds.
Yeah,
okay.
To be loaded. Okay, so before
there.
I hope so. So before my screen will be shown, so I will just quickly introduce, let's say, outline of my part. So first, in the first part, I will present or introduce the input requirements. So I think now it's coming.
Yeah, we can see it now. Yes.
Okay, perfect. Thank you. Okay, so in the first part, I will introduce the inputs. So the inputs requirements, basically inputs requirements on the geometry, on STLs, which are automatically generated and followed by the CFturbo export. So if you use CFturbo as a kit tool or as a design tool, so then you will immediately, by one click, as Oliver already shown us, that by one click you can generate the export to TCFD and then use it in TCFD. And then in my second part, I will show you some live example of this radial fan. So what is the TCFD workflow? So we can split it into parts, two main parts. First one is the input, which is a little bit a part of TCFD. So it's the input data. So usually you need to create your geometry in some kit software, then you export the data into STL format, which is triangulated surface format, or using some external meshing tool and directly generate the simulation ready mesh in, for example, MSH format, and then put it into the TCFD and simulate it in TCFD. So there are two main inputs, STLs or mesh, which is ready to simulate in MSH format. Then we need to prepare the simulation parameters, which can be directly set in the graphic user interface of TCFD, or you can prepare it apart in the text file because it is just a file including simulation parameters. You need to be aware of garbage in, garbage out, of course. So if you put something wrong inside, then of course you will get the wrong results. So So what I would like to just mention that TCFD is not yet a tool for CAD to STL data conversion. So the geometry must be ready apart from TCFD. And then the TCFD's workflow is basically loading the data, loading the geometry, preparing the CFD simulation setup, so configure all the parameters like simulation type, for example, fans, compressors, pumps, and so on, rotation speed of the impeller or propeller, setting boundary conditions, setting physics, setting how many processor you want to use, and so on. Then the processing part, so basically really the simulation and all the stuff around the simulation, and at the end it automatically generates a report including all at one place, so all the variables, all the properties, all the parameters of your design, like efficiency, torques, axial forces, and so on. So this is the workflow of TCFD, and I would like to really emphasize the input requirements which has to be satisfied. So basically a lot of them must be followed both for STL geometry or external mesh. So first one is the flow path geometry. So we need to define just the fluid solid interface, so called the wet surface area. Of course, you can provide the full solid, but the full solid must contain the flow path area, the wet surface. So this must be provided, of course. Then the geometry must be as simple as possible, because any detail, any tiny hole which usually doesn't affect the overall parameters of your machine, of your geometry, should be neglected, because it only makes trouble and doesn't improve anything. So as simple as possible. Then you should think in a component. So basically it follows the component thinking which Oliver has already shown us. So basically your geometry can be split into rotors and stators, into volutes, pipes, impellers, propellers, and all these parts. And then these parts are defined separately and then put together to define the rotating parts and the non-rotating parts properly. So the component thinking, then to think you need to provide physical boundaries. So you need to provide separate parts of each component. For example, you need to split your component into inlets, outlets, hubs, shrouds, blades. The blades can be additionally split into, for example, leading edges, trailing edges, pressure and suction sides, and so on. So this physical boundaries has to be defined. And of course the water type property, because the meshing tool needs to have the water type property, or at least the holes must be really tiny to generate the computational mesh properly. So water type property and the triangulation refinement, which is a discretization of, for example, of a CAD, of the continuous CAD geometry. So the triangulation has to be as fine as possible, because this is what you define your domain. So if you input something like this, then you basically you have something different from the real design. Yeah, so the triangulation must be as fine as possible. So this input part can be altered by CFturbo, because it generates exactly the geometry which follows all these input requirements. So by one click, you can get the inputs into TCFD and then use it for TCFD simulation. As well as CFturbo also generate automatically the templated configuration file with all necessary and with all preset and necessary parameters for successful TCFD simulation. So what TCFD exports? So it is a geometry of the impeller, split it into meaningful parts like inlet, outlet, hub and shroud, and the blades split it into 4 parts: trailing edges, leading edges, and pressure and suction side. And the same for the volute. Volute is again split into the inlet, outlet, and then the rest part of the volute, like tongue area, outlet diffuser, the body of the volute, and so on. And the last part, it generates configuration file. So it's a simple file including the TCFD's parameters, like what is the axis of rotation, what are the physical properties of the fluid, and so on. So everything is ready for the simulation. So I will go now for a live example. So I will go for CFturbo export. So I have this data here. So I will just to open it in TCFD. So this is the input geometries in STL format and the configuration file. So what I need is only to click on the configuration file, and the new graphical user interface will appear. So it automatically loads the input geometry, and then we can briefly present the setup of TCFD simulation. So this is our input geometry, split it in 2 components, impeller and volute. So here are the menus which is used for the TCFD setup, for the simulation setup. So I will go just quickly. In the simulation part, we set the time management, so steady state or transient simulation. So here we will simulate steady state, how many processors. For example, my computer here has 16 processors, so I can use all of them. Numerical order, first or second. You can go for second, for example. Convergence check is just checking for the convergence, if the convergence or convergence conditions are satisfied, it stops the simulation before the maximum iteration are reached. Physics, we can set reference frames. Using in the reference frame, you basically define the rotation, the rotation of your of the impeller. So by setting axis, origin, and the rotation speed. Now the component section, which is pretty important. So here you basically define the mesh, the computational mesh based on the input geometry. So we have 2 components, impeller and volute. Impeller is rotating, component is static. And for each part of the geometry, we set basically the type of the boundary, which is really straightforward. Blade, there is a type blade or blade leading edge, blade pressure side. There are types like hub and shroud, inlets and outlet interface. So simple inlet is the physical inlet into the whole geometry, and something inlet outlet interface is the connection between two components. Then you need to set the refinement, so how fine the mesh will be at the given parts of the geometry. Maybe here I will use my presentation. So here are the meshing parameters. Basically, the coarsest cell is defined as a background mesh size. So this is the coarsest cell in your computational mesh. And then you set the level of refinement. So how many times the mesh will be refined at each part of your geometry. So level 0, level 1, level 2, simply splitting of the hexahedras. What I would like to mention here, that it is really handy if you split your domain, or for example your blades, into meaningful parts, for example leading edge, trailing edge, and pressure suction side. For usually, if depending on the case of course, but usually you need for highly curved and thin blades, you need to provide really really refined mesh at the leading edges and trailing edges because of high curvature. So you need to provide more cells to really follow the geometry. So for this purpose, if we set the level 2, for example, here for the whole blade, we get something like this. So the leading edge is very coarse and this zigzag shape, which is not good for the simulation. So if we set the level 4 everywhere, so we have, let's say, nice refinement at the edges, but also at all the blades, which generate us much more higher cell amount in your mesh, which also makes the simulation much more longer and so on. And for example, the Y plus requirements are not so high. So we can then decide, okay, I would like to just refine the leading edge and trailing edge, and I can keep a coarser level at the pressure side and suction side, and we save a lot of cells. Yeah, so if we export it in this way, we can really tune the meshing to have really nice meshing with a less amount of cells compared to the export with the blade as a one STL, for example. So this is really handy. So thanks to this, we can play with these numbers and set it to follow our needs. So this was just quick introduction into the meshing part. Then the rest section are, for example, the speed lines. So within the one simulation, you can define more points. So to reveal, for example, the full performance map with the different conditions, usually the different flow rates, for example. So CFturbo exports the best design point for which the design was designed. A lot of design words. So for example, I can add, let's say, 5 points to be simulated. Let's say with the maximum number of iteration 1000. Then turbulence model is here K omega SST. But then in the boundary conditions, so at the inlet we set the volumetric flow rate, and at the outlet there is the fixed pressure. So we know that this value is from CFturbo, and this is the best design point. So I will put it into the middle, and I can, for example, simulate the points around the design point by the percentage, for example. So I can set something like this, and if I change the items here, so this plus percent sign, which means that I will simulate the volumetric flow rate, which is increased by 20% compared to this value, and similar for the rest. So I would like to reveal the properties of this design around the design point. So I can use it in this way or using the absolute values of volumetric flow rates. It doesn't matter. The initial condition and some simulation controls for the solver, and the post-processing, in which I can set my favorite units, which will appear in the final report, which parts will be used for evaluation of the efficiency. So now it is set for the full geometry, but I can also add efficiency probe, we call it. So basically from which part the efficiency will be evaluated, and I can set, for example, just for the impeller. So I will get rid of it. So just I would like to see the efficiency of for the whole geometry. Additionally, I can preset some automatical evaluation features, which is blade-to-blade views, for example. So I can generate, for example, 3 blade-to-blade views with the visualization of, for example, relative velocity with streamlines. So I can just simply click here, and this is span. So it is basically it is a slice between the hub and shroud, at the relative coordinates between hub and shroud. So this is it is the coordinate 10% of overall height close to the hub. This is just in the middle, and this slice will be in the next to the shroud. Similarly, I can set up the meridional average. So for example, I will set 2 evaluation, one for total pressure and one for static pressure. And that's all. Whenever I am done, I can go for the simulation. So if I know the settings, I go for TCFD manager. Then I can click apply. I have to click and apply, of course. Then define the name of the directory in which all the results will be stored. Then I can click write case and run all to run all the simulation, all the process by one click. So whenever I'm not going to do that. So by run all, I will run everything which I have done before the webinar started. So this is the progress of the simulation. So here we can see the residuals. Here we can see the light report, which can be generated anytime during the simulation. So including the updated values of my simulation up to now. Meanwhile, I can, for example, or anytime after the mesh is generated, I can visualize the mesh by clicking here and for example, to see the topology of the mesh at the volute, right? And at the end, the full report is automatically evaluated. Moreover, at the end of the simulation, anytime you can open the results. Okay, so I can go back. You can open the results by the show results, or anytime later on, if you go to my directory or to your directory with your simulation, and by clicking on the case foam, you will open the case with all the results, and you can make some manual visualization. For example, here I have two blade-to-blade views, one with static pressure contours and one with total pressure contours. So it was my clock that my time is almost up. So I will quickly conclude. Yeah, so there is no limitation. You can do any visualization as you want and analyze your geometry and your simulation. And maybe the last part, what I would like to mention, is some introduction to the newest release, which is under heavy testing at the moment. So there will be, for example, new transient options, which allows us to define any time stepping, constant time stepping with following the degrees of revolution of the wheel, which is really handy. You can then compare the results. For example, here's comparison of the steady state of this radial fan with the transient simulation. You can see there in the report, and yeah, and many other features will be introduced. So I think my time is really up. So I think, yeah, I'm at the end. So thank you for attention, and it's time to go back to Luboš to conclude this webinar. So Luboš, can you take over the presentation back?
Yes, of course, Radek. Okay. Thank you very much for your part of the webinar. So I'll take back the presentation, and yeah, and we are nearly done. Yeah. So now it's the Q&A time. So I would like to ask all the audience, if you have any question, just ask the question. We will answer a few of them, and later we will answer all of them. So feel free to ask your questions, and it will be our pleasure to answer them. Okay, so does anybody see a proper question who would like to answer? So yeah, so James is asking, what post-processing tool did you use? It's ParaView, right? So maybe you noticed, or it's pretty known that TCFD use ParaView for its case setup, case run, simulation run, and the detailed post-processing. So yeah, it's ParaView. Okay, so does anybody see a question to answer? So yeah, so yeah. Yeah. Maybe we can answer this one. So for example, Kasse is asking how we can control the criteria of quality meshing. So Radek, would you answer a little bit what we can see in the report of every simulation? For example,
yes, I can.
The stats?
Yes, yeah, I can. So just if you can give me the
Yes.
presentation.
Yes.
Okay, show my screen. Okay, maybe there will be again a delay, unfortunately.
Okay,
So,
the delay again. Oh.
okay, so
Okay.
meanwhile I will find the report, and maybe you can answer.
Yeah, answer another question.
If there is
Okay.
some.
So I have to say, so far I can't see many questions on CFturbo, and I can't see any question on TCFD either. So maybe it's, I think maybe it's time to, or Radek will show. Okay.
Okay,
Show the
it's
report
there.
and mesh stats,
So,
then we
okay,
conclude.
here is the report. So I will open the report. So it contains, let's say, almost all the parameters of the simulation, including the mesh statistics. So there are all the standard meshing parameter like non-orthogonality, skewness, and so on, and you can follow its values directly here. Yeah, so for the component 1, for the component 2, all the parameters, all the meshing parameters are here. Yeah, so everything is available for each simulation.
Okay. Thank you, Radek. So yeah, so this seems to be it. So the time is gone anyway. So I think it's time to conclude. I'll switch to the end of my presentation, which is this. Okay, so yeah, this is really it from us in this webinar today. So yeah, thank you for coming. Feel free to contact us. I'm sure you know how to do that. The questions about CFturbo are to be sent to CFturbo. The questions about TCFD are to be sent to CFD support. So let us know how we can support you. We will gladly support you in your projects. It's our job and also our pleasure. And yeah, this really seems to be it. So anything more to say, Oliver?
The only thing I want to say is thank you for your time, and hope you will be at our webinar next time again. Thank you and bye-bye.
Thank you. And Radek?
Yeah, I think everything was already mentioned. So thank you for watching us. Thank you, Oliver, for joining this webinar. And I will also looking for the next webinar, and I will also looking for the question from the attendees of this webinar. So have a nice day and bye bye.
All right then, so we leave you with that. So thank you for your attention. We are looking forward to collaborating with you. Stay tuned and bye bye for now.